Okay, is this working? Hello, 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 hello. Ooh, okay, everything's different. OBS has changed. YouTube's changed. Can you hear me? Can I see me? Working. Hello, hello. Yeah, okay, that sounds good. Um, so I was inspired to do this because I was watching Andrew Dotson, who I completely recommend you go and watch. Also on Papa Flammy, who's a mathematician. They kind of do uh, episodes together, and they're very funny and just inspiring and kind of get you motivated to do some maths and physics and stuff. Um, so Andrew Dotson actually had a live stream just a few moments ago, and I apologize up front if you ever watch this. I really wanted to interact with you about the Schrodinger equation and maybe even more so the Dirac equation, but uh, the format wasn't quite right to keep asking questions, right? So, but you said something interesting, and I think it makes me realize I should go back to the drawing board and ask myself, do I really understand what the idea of these two equations are? To summarize for new people, not that there's any old people here, um, I want to know where positions of electrons are, and I don't mind having a probability of where they are, at any given moment in time. And this will allow me to know the mass and force interactions between those electrons, and in turn, how they affect the folding of a protein. That's what I want to know. I understand AlphaFold's done this. This is Google's company. Um, I will be using their software. I need to understand it first before I start using it. So, with that all said and done, I thought I would just recap over what Andrew said in response to my question, which was poorly put together. I apologize and thank you, Andrew, for responding. And at the same time, also I've been looking at a video that may be of help. I'm not sure. It goes quite heavily into maths quite quickly, as if I should know what these things are. So I'm going to have a look at them in a bit more detail. Having said that, this is 30th episode, so clearly a celebration of the 30th episode. I don't know why. It should be 100, right? Anyway, yeah. Unfiltered Stellar Artois. Why not? I've had a few of these already, so I apologize on the quality of this stream, as always, but this is how I roll. Yeah, it's a nice beer. Okay, cool. Right, so I hope you don't mind. I'm going to just play this little bit. This is thanks, Andrew. Really appreciate it. Just about to stream myself, in fact, to think about what you and Solaire. This is another person who has given me great insight into some things just to think about. What they say about the Schrodinger equation, and keep up the great work. You are an inspiration, and I really appreciate it. Here we go. Let me actually just test if this comes through correctly. So bear with me. You are an inspiration, and I really
Second
appreciate
attempt
it.
in turn.
Here we go. Let me actually just test if this comes through correctly, so bear with me. You are an inspiration, and it does. Okay, cool. So I just played it and just made sure that I could hear it. So this is what he responded to my question.
In terms of actual data you pass in, what do you pass into the Schrodinger equation's wave function part?
Hmm.
Well, that's the
So let me just remind myself. This I think he puts it down anyway. But let me remind myself. Settings Google has changed some of your settings for this site because you aren't confirmed to be over 18. Okay. So Schrodinger equation. Let's get this up. So here is the Schrodinger equation, and I asked, well, we know what the complex part is. This I. We know h is the Planck's constant. We know this is a differential over time. But here is the wave function part with respect to time. And so, if you think about it, you want to use the equation to kind of get an answer out. What is it that you put in? Now I think it goes into great detail here in this week article, but we've gone through this many a time. I think the understanding of what they're trying to tell me is missing. And so this is why I asked the question, what is it that you put into the wave function? And this is the response.
The solution. Um, so for the Schrodinger equation, I don't know, why not, right? See if I can. Minus h bar squared over 2m del squared psi minus v psi equals I h bar d psi dt. This is just
So let me just compare this, make sure we're talking about the same thing. So we've got this IH. He's gone negative, but it's over the change squared of the wave function minus v. So it's a slightly different form of it. Let's go see if we can find that form first. Let's see, where's the negative here? Okay, so there's nothing up front that says about that. Oh, excuse me, that style of equation. So let me just try and understand what's happening here. So it's a negative of the area of Planck's constant. So, okay, divided by 2 times the mass. 2 times the mass of something. So it's h. So Planck's constant squared. Ah, no, the bar of h squared, whatever that is, I can't remember. I think it's Planck's constant, but it's something else, part of it. It's the area divided by 2 times the mass multiplied by the. So this is not the delta symbol, this is the inverse thingy. Delta symbol, I think that's upwards. So upside down, I can't remember what it means. Del operator. The gradient of a function produces a vector. The gradient of a function produces a vector. So in this case, the gradient function that produces it, so the vector squared for that gradient multiplied by the wave function minus the velocity multiplied by the wave function is equal to the Schrodinger equation's right side. Ah, no, but I have seen this. Yeah, here we go. H bar differential of t. But he's got wave function here as well, so I guess is actually what this means, I think. I might be wrong, but I think I remember seeing that if you just put this over here, that's kind of what it's saying. And this n is interesting. But if this one is h hat rather than h bar. Let's just continue here. So we've got minus the velocity times the wave function is equal to. So he says it's the solution. The wave function is the solution. But actually, this is the wave function that you have in it. So, because if I look for this notation here, it does actually say here, psi is a wave function. So psi of x t is a wave function. A function that assigns a complex number to each point x at each time t. So that function takes the x, assigns a complex number. I'm not sure what that means yet, although I'm aware of what a complex number is. And it does it at each point t. Oh look, we found it. Look, this is it. So minus h squared 2 over m multiplied by the Ah. Okay, so let's see if we can rework this a bit. Let's go for paint. Why not? Oh, so white there. So much on your eyes. So if I were to take this equation here, can we rework it into the other one in Wikipedia? If so, we understand. If not, ooh, I'm not sure. God, that looks like an A. Okay, so we need to get it. Let's imagine we want to get it into something like this. Let's take a little screenshot of that instead. Should have done that with the other one, really. So we want to get it into that. So first of all, the I. So this is I. See, this is the other. This is the other way. Okay, fair enough. So this is here, and I think that is just respect to time. I think that's what this means. It's funny that it's bracket, but um, I'm not sure I understand that. But it's equal to this. He's saying so. H hat wave function of t is very different, isn't it? I wonder if there's just reworkings of it. So I really would love to understand this without having to go through the half and puff of it all. Modern physics, what does this say? Ah, now this looks a little more familiar, maybe. AH, we've got the partial with respect to t, and this, no. But we did find down here the h squared over 2m. So here we've got the h squared over 2m. So this gradient squared, gradient vector squared, and why is it plus rather than minus? Yeah, not sure. Not sure I understand it. Okay, and let's see what he says, because I thought it was rather interesting actually.
I don't know if you're asking like what do you do with the wave function here, but that's what you're solving for. You say what is the function psi that is that satisfies when I take its Laplacian weighted by this term and I subtract the potential times the function, I get its time derivative times IH bar. So I'm
I get its time derivative times h bar. Laplacian. Laplacian. So this is why it's awesome to ask. Thank you, thank you, thank you. Just more words to learn. Laplacian is a commute. No, no, I don't know how to spell this. So I've got a Laplacian operator. A derivative operator which is used to find edges in an image. The major difference between Laplacian and other operators like Pruitt, Sobel, Robinson, and Kirsch is that these all are first-order derivative masks, but Laplacian is a second-order derivative mask. In this mask, we have two further classifications. One is positive. Who writes this stuff? Like, who are they talking to? There must be an easier way of explaining this stuff. Must be. What does Laplacian mean? Flux. What is flux? The action or process of flowing or flowing out. So it's motion density of the gradient flow. Gradient flow. fluxes of the gradient flow of a function. In mathematics, the Laplace operator or Laplacian is a differential operator given by the divergence of the gradient of a function on Euclidean space. In mathematics, the Laplace operator or Laplacian is a differential operator. Well, we understand that. It's an operator that works over change. Given, it's given by the divergence of the gradient of a function on Euclidean space. Given by the divergence of the gradient of a function on Euclidean space. This is how much given by the divergence of the gradient. So that there is a gradient, and it's how much it diverges from that gradient on Euclidean space. It is usually denoted by the symbols squared. So let's go look at our. Okay, fine. Yep, those add up. That Laplacian, the change in f of a function, f at a point P, of a function f at a point P. So the function is applied to a point on Euclidean space up to a constant, depending on the dimension, is the rate at which the average value of f over spheres centered at P deviates from f as the radius of the sphere grows. In our Cartesian coordinate system, the Laplacian is given by sum of second partial derivatives. Okay, too much again. So let's listen into the last part.
Asking what is the function, what is a function that satisfies that, and you can't answer that question until you have the potential. So that's like the crucial piece of data you need. You need a potential. This is a second order differential equation. So integrating twice, that's two constants of integration. So you also need two initial conditions.
You need two initial conditions. Ah. Okay, I see.
Two initial conditions and I guess two boundary conditions and one initial condition. This is a partial differential equation.
Yes, understood.
But usually this part is trivial. You solve it once. What is with all the workout questions?
I think that was it. So that's what I was told. I'll have to listen to it again. But once again, I really appreciate you just taking a look. Thank you, man. Thank you.
Second attempt. In terms of actual data you pass in, what do you pass into the Schrodinger equation's wave function part? Well, that's the solution. So for the Schrodinger.
So he's saying the solution is the wave function. The solution is the wave function. So that's interesting because I think I'm misinterpreted this. So let me just go mostly because the wave function here, x of t, is a function. So what does the function do? Well, okay, right. So the Schrodinger equation is a linear, straight-lined, partial differential equation. I think that's what that means. That governs the wave function. It's a linear partial differential equation that governs the wave function. What does that mean? It it's a partial differential that tells you what the wave function is going to be. Ah, I see. Yes. It is a key result in quantum mechanics. And its discovery was a significant landmark. The development of the subject. The equation is named after who we know. Okay. Conceptually, the Schrodinger equation is the quantum counterpart of Newton's second law. Let's just remind ourselves what the second law is. F equals ma. F equals ma. The force. Ah. Oh, I see. It's not giving us the position of x. It gives us what it's saying is conceptually the quantum counterpart of F equals ma. Given a set of known initial conditions, Newton's second law makes a mathematical prediction as to what path a given physical system will take over time. And that's interesting because if the second law is F equals ma, then the forces acting upon it would denote where something will be in its next frame of reference, is how I understand what I'm reading there. Such dense information, isn't it? Gosh. The Schrodinger equation gives the evolution over time of a wave function. This makes sense. So over time, something's changed in the wave evolution over time of a wave function. So something has changed, not in the wave function, but it's the result of the wave function. So the Schrodinger equation gives the evolution over time of the result of a wave function, I think, is what that means. The quantum mechanical characterization of an isolated physical system. The quantum mechanical characterization of an isolated physical system. The equation, what does that mean? The Schrodinger equation gives the evolution over time of a wave function. The quantum mechanical characterization of an isolated physical system. Okay, I think I conceptually understand what that's trying to say. The equation can be derived from the fact that the time evolution operator must be unitary and must therefore be generated by the exponential of a self-adjoint operator, which is the quantum Hamiltonian. This part, I have no idea what that's saying. The equation can be derived from the fact that the time evolution operator, okay, must be unitary. A unitary operator is a surjective bounded operator on a Hilbert space that preserves the inner product. Unitary operators are usually taken as operating on a Hilbert space, but the same notion serves to define the concept of isomorphism between Hilbert spaces. Let's get a picture up of a Hilbert space. let's see if we like something else helps here. A Hilbert space is a vector space, okay, H, with an inner product such that the norm defined by the magnitude of function is equal to the square root turns H into a complete metric space. What the fuck am I reading? A Hilbert space is a vector space H vector space with an inner product right. Okay, yeah. So let me. So inner product. Inner products allow formal definitions of intuitive geometric notions, such as lengths, angles, and orthogonality. Zero inner product of vectors. Oh, why? Why is it so hard to understand what people are trying to bloody say? In mathematics, an inner product space, or rarely a Hausdorff pre-Hilbert space, is a real vector space. Or a complex vector space with an operation called an inner product. The inner product of two vectors in the space is a scalar. So the inner product, so the multiplication of two vectors, is a scalar, often denoted with angle brackets such as, oh, that's interesting. So the inner product of two vectors in the space is a scalar, often denoted by that. Inner products allow formal definitions of intuitive geometric notions, such as lengths, angles, and orthogonality of vectors. Inner product spaces generalize Euclidean vector spaces, in which the inner product is the dot product or scalar product of Cartesian coordinates. Inner product spaces of infinite dimension are widely used in functional analysis. Inner product spaces over the field of complex numbers, I have to remind myself what this is in, a set on which addition, subtraction, multiplication are defined and behave as the corresponding operations on rational real numbers do. The field is thus a fundamental algebraic structure which is widely used in algebra. It is a set on which addition, subtraction, multiplication, and division are defined and behave as the corresponding operations of rational real numbers. Inner product spaces over the field of complex numbers are sometimes referred to as unitary spaces. The first usage of the concept of a vector space with an inner product is due to Giuseppe Peano in 1898. So let's go back to this. Where are we? This one. So the equation can be, the equation can be derived from the fact that the time evolution operator must be unitary and must therefore be generated by the exponential of a self-adjoint operator. In mathematics, a self-adjoint operator on an infinite dimensional complex vector space V with inner product is a linear map A that is its own adjoint. If V is finite, wait, hang on. Let's get the etymology of adjoint. To join up. It is literally adjoint. To join up, okay. The Schrodinger equation is not the only way to study quantum mechanical systems and make predictions. The other formulations of quantum mechanics include matrix mechanics, introduced by Heisenberg, and the path integral formulation, developed chiefly by Richard Feynman. Paul Dirac incorporated matrix mechanics and the Schrodinger equation into a single formulation. When these approaches are compared, the use of the Schrodinger equation is sometimes called wave mechanics. Okay, so what I'm going to do is I'll listen one more time to what's being said, and I think I'm going to start like watching the other video that I talked about. Um, I might not go the whole way through, obviously, because it's like an hour long. But I'm interested to know, or at least start to reignite some of these thoughts in my head about how all this stuff works. I have been thinking about it quite a lot. I feel a bit stuck. I feel like I've got another barrier of mathematics and physics to break through. Um, I did some work, I think I said already, in Finland, the place where I went on holiday, to uh, to to kind of lay out the code for the application, and I got stuck. So this is a good place to kind of whirl about a bit, but I need to understand this properly to be able to go forward. So after that, I'll do a quick Greek lesson because I didn't do it at the beginning. So that's what we're gonna do.
Second attempt. In terms of actual data you pass in, what do you pass into the Schrodinger equation's wave function part? Well, that's the solution. Um, so for the Schrodinger equation, I don't know, why not, right? See if I can. Minus h bar squared over 2m del squared psi minus v psi equals I h bar d psi dt. This is just, I don't know if you're asking, like, what do you do with the wave function here, but
Just if you do see this video for some weird reason, I was expecting that. So I'm not aware of this layout of it because I'm pretty bad at everything. But if I talk about the Schrodinger equation that comes in Wikipedia, um, I was expecting that part of this equation would require you to input the wave function. So in respect to t, so I was kind of wondering what is the data that you pass into that part of the equation. But actually, just from what you said, I have to tell myself that no, this is simply denoting an equality between two things. It does not necessarily mean that it's going to give you something. It just simply means that there is an equality between two things. Um, Maybe that helps me, but also that you're saying that it's the solution to it. So that means that um, the solution to the whole thing. This isn't your fault, by the way. It's just I should go. I really just go to university and learn this bloody stuff, but I won't. So
that's what you're solving for. You say,
you're solving for the wave function. You're solving for the wave function.
what is the function psi that is that satisfies when I take its Laplacian weighted by this term,
If I take its Laplacian weighted by that term, if I take its Laplacian weighted by that term,
and I subtract the potential times the function,
and I subtract the potential times that function.
I get its time derivative times IH bar. So I'm
I get its time derivative by IH times.
potential times the function. I get its time derivative times IH bar. So I'm
I get its time derivative by times by IH bar.
asking what is the function, what is a function that satisfies that, and you can't answer that question until you have the potential.
What is a function that satisfies that? Ah, hang on. That does make sense what he's saying. So it's not saying anything to do with what I thought it was saying. Unless, maybe this is saying if I had some form of data already, it must it must take it must satisfy this equation, whatever that actually means. Okay.
So that's like the crucial piece of data you need. You need a potential. This is a second order differential equation. So integrating twice, that's two constants of integration. So you also need two initial conditions. Two initial conditions, and I guess one.
Right. I see. I see. He's saying that I need not only. I think this is what he's saying. Is it over time? So if I've got two frames, I need because it's like a differential. I need to because I need to do one loop to get the next part of the variable value. This means that I need one position to the next, or one potential to the next. It could be what this meant. It could be. I don't know. We'll see.
Sorry, two boundary conditions and one initial condition.
Two boundary conditions and one initial condition.
This is a partial differential equation.
Two boundary conditions, one initial condition. You're saying between two things. And at what time?
But usually this part is trivial. You solve it once.
That's trivial, you solve it once. Okay. Well, okay. Um, so I'll leave this. I'll leave this here for this video. I think I've taken what I need from this in terms of like paths opened up. Um, Once again, I really appreciate you responding, really, and also some chap called or chapess called Solaire, who was helping kind of guide me and um, give me things to think about. I think one of the things that was said was there is one wave function for all the particles, but there are methods to approximate this as a superposition of constituent atomic and electron wave functions. It's saying there is one wave function for all the particles, but there are methods to approximate that with constituent atomic and electron wave functions. Something like a Fourier, Fourier sequence, whatever it is, Fourier series, where you're like adding wave functions together to approximate that wave function. So if I don't know if I'm speaking bollocks here, but if if there's a wave function for all the particles, what do you have to join up in terms of waves to form that one wave function for all particles at a time between two potentials? Is that what's being said here? Is that helpful to me? Is the question. Is that actually helpful? Potential. So I need to know the positions of things, but also the potential is energy. That's F equals ma. Oh, I see. It's saying how much is the net force on that? What's the potential of that, whatever that is? Now, if I have the energy, I do not have positions of electrons. But I do have the energy available at a given point. I wish someone could just confirm that what I'm thinking is right here. But that starts to make sense if that's the case. So, okay, thank you once again. So this is the video that I started watching. I think got about to about 10 minutes in, and I thought, oh, it's quite heavy on equations and stuff. So, thanks, Physics Explained. A little heavy going, I have to say, but I think I want to piece it together. So here is another version of the Schrodinger equation. H times the wave function is equal to this. I've seen this quite a lot. Uh, I've seen this quite a lot. I haven't seen this ever. So I'd be interested one day to know how this is rearranged to get to that. Let's start this
One of the
video.
most famous and important equations in physics, the Schrodinger equation.
Mhm.
It's an equation that lies at the heart of quantum mechanics, and it forms the basis of much of our modern understanding of the universe. But what exactly is the Schrodinger equation, and how can we use it to perform quantum mechanical calculations? In this video, I will provide an introductory overview of Schrodinger's equation, with my aim being that by the end, you should hopefully be ready to pick up an undergraduate textbook on quantum mechanics and actually enjoy the experience. So if you're up for the challenge, stay tuned.
We're up for the
Our
challenge.
story begins in Vienna when on the 12th of August,
Yeah, actually, a lot of this.
that's paper that a footnote Roy, who had read this copy of de Broglie's thesis. What was particularly exciting for Schrodinger was that de Broglie had dared to ask the question that if light waves can behave like particles, as has been shown by Einstein's explanation of the photoelectric effect, is it then possible that particles such as electrons can behave like waves? De Broglie's answer to this question was an unequivocal yes.
An unequivocal yes. Can electron waves act like electron particles? My understanding is that there really isn't a particle. Everything is a wave. I think that's probably wrong, given the never-ending explanation of things in a particle sense. Though, then again, when I think about all the kind of lectures that I've watched, it really does speak about everything being waves in terms of the energy and how it moves around is the interaction between waves. What that really means, I guess I don't know. Waves are some expression of the physical world, some abstraction of it. Do I put so much weight on it to separate myself from having physical things in one place and that they move and act upon each other? I guess so, because everything at a very small level seems to have this probabilistic position, making things difficult to predict where the next step for that particular element will go. Okay, so let's go with me thinking that everything is made of waves. So that's really interesting here, because Schrodinger is saying the electron particles can be represented by waves. Let's get the wording again. What does he say?
Of the photoelectric effect. Is it then possible that particles such as electrons can behave like waves?
Behave like waves. Can electron particles behave like waves? And the answer is unequivocally yes.
De Broglie's answer to this question was an unequivocal yes.
Okay.
In summary, de Broglie proposed that for a matter particle with mass m moving at
a matter particle, let's draw this down. So this is what I needed to do when I originally watched this. So it says, oh, I can't stand this white here. It's so bright. So he says,
in summary, de Broglie proposed that for a matter particle with mass m moving at velocity v,
a matter particle, so here it is, of mass m, so let's say that, mass m, moving at a velocity of a v,
you can associate a plane wave of wavelength lambda equals h over p, or h over mv, where p equals mv is the momentum of the particle, and h is Planck's constant. For
right.
mv moving at velocity v, you can associate a plane
wave, of wavelength, associate, so I won't say equals at the moment, excuse me. So yeah, let's put some little squigglies here, some little pubes. Associate lambda is equal to h over p, which is equal to h over mv. Okay, well this makes sense. So p is momentum. So p is momentum, and we know p, or momentum, is equal to the mass times the velocity, or mv. And so he is saying in this case that h divided by, so is equal to, so he's saying that h, which is Planck's constant, divided by the momentum, is exactly equivalent to h over mv, which makes sense. This makes sense. And he's saying that lambda, an abstraction or a variable name, is equal to this. So he's saying if we take lambda to equal h of Planck's constant over p or equal to h over mv,
plane wave of wavelength lambda equals h over p, or h over mv, where p equals mv is the momentum of the particle, and h is
momentum of the particle. Right, so where p is a momentum of particle.
Planck's constant. Furthermore, if the particle has energy E, then you can assign a frequency given by
If the particle has energy E, so let's do this like 1, you've got 2, 3. These are just, I'm just labeling how I discovered these things or thought about these things at least. So saying that if each particle,
if the particle has energy E, then you can assign a frequency
if the particle has energy E, so if particle energy is equal to E, okay,
given by F equals E over H, and these relations connect the particle concepts of energy and momentum E.
now he's saying rather than E it's capital E, okay, so let's go with that. Capital E because the energy is a set. I don't know why it's capital E. So if the particle energy is E, and we have a function that is equal to E divided by the Planck's constant. So the energy is equal to, no, the energy divided by Planck's constant is equal to the function. So this is a function, okay.
And P, with the wave concepts of frequency and wavelength, F and lambda. Now what de Broglie did
So it says particle concepts, energy, momentum. Energy is the same as frequency, and momentum is the same as wavelength. Whoa, okay. So energy, okay, well that's fine. So so energy is the same as frequency, and momentum is the same as wavelength.
was simply assume that these two relationships hold for all matter particles, including electrons. Although there was no experimental evidence at the time to support de Broglie's hypothesis, he was encouraged by the fact that he was able to
Hypothesis. So he assumed that these two were equivalent. Energy is the same as the wavelength, and frequency is the same as, oh, I've forgotten already. Energy is the same as the frequency. So okay, so this seems relatively important. So let's delete this then, or let's document this at least. Let's do that. Let's go to our OneNote. Let's go to episode 30. So this is in regard to this video. Right, so he's saying here this. This is a concept that Broglie had hypothesized.
including electrons. Although there was no experimental evidence at the time to support de Broglie's hypothesis, he was encouraged by the fact that he was able to provide an explanation for Bohr's model.
De Broglie. Oh, I can't remember how I said now, but this is Broglie. Oh, de Broglie, something like that.
model of the atom. Although other physicists had taken a passing interest in de Broglie's work, the lack of experimental evidence dissuaded most from spending too much time thinking about the ideas.
Now, this is interesting because we know from our studies that uh, these n's are the well, I can't even remember now. N is the is the shape, orientation. Goodness knows what. Let's see if I've got this back here somewhere. Pretty sure I do actually. Yeah, the principal quantum number n a shell. Um, okay, well, I mean, I can't quite remember, but I'm guessing it could be a shell, given the range here. But this is saying the energy, the total energy is equal to negative a 13.6. Oh, where's 13.6 come from? Black constant. 13.6 watt over n squared multiplied by energy times velocity.
However, when Schrodinger read de Broglie's paper, he immediately wrote to Einstein to share his thoughts about the implications of wave-particle duality.
So this is saying that the total energy is equal to the negative of 13.6 over n squared times the energy times the velocity. That's a good little find.
A couple of weeks later, Schrodinger was asked by the physicist Peter Debye to present a talk on de Broglie's work at a physics colloquium in Zurich. Schrodinger gave a beautifully clear account of de Broglie's work. However, not everyone in the audience was convinced. In particular, Peter Debye did not like the fact that according to de Broglie's theory, there appeared to be matter waves, but no wave equation to describe these waves.
There seem to be matter waves, but no wave to describe these equations. Let's just make sure I heard that right.
Peter Debye did not like the fact that according to de Broglie's theory, there appeared to be matter waves, but no wave equation to describe these waves.
No wave equation. So there is matter waves, but there's no way of describing those waves. So you didn't like it simply because there was missing work, I guess.
How can you have a wave without a wave equation? According to the well-established classical laws of wave motion, any wave, whether it's a sound wave, electromagnetic wave, or wave on a vibrating violin string, has an equation that describes its motion. However, in de Broglie's theory, there was no wave equation. De Broglie had never attempted to derive one, and neither had Einstein. Schrodinger knew at once that Debye was correct. You cannot have waves without a wave equation, and almost at once he decided to set himself the task of finding the missing equation. And in the space of only a few months, Schrodinger was able to take de Broglie's tentative ideas surrounding wave-particle duality and develop them into a fully blown theory of quantum mechanics. In the remainder of this video, I would like to provide a simplified overview of Schrodinger's theory.
Okay. Yeah, this all makes sense. So I see. You know, it even rings true with what Andrew was saying, which is um, he says that the Schrodinger equation solves for the equation. It gives you the wave function if you have momentum and something else. Um, oh, I see. Okay. I see. So this is starting to glue together quite nicely actually in my head. Um, good. Once again, thanks Physics Explained. Please check out their channels, Physics Explained and Andrew Dotson. Andrew is so funny in his videos. Um, has interesting topics like he was uh like having a week with some kind of younger students and showing that kind of process of how he interacted with the students and what they did and stuff. Excellent content. Go and watch him. It's really cool.
We will begin our investigation with a simple review of the properties of classical waves.
Yeah, and this is important. I think in the last video I was actually thinking, what is a cosine? What is a sine? What is tangent? Because these calculators are doing um, mathemat mathematical computation underneath the hood, and I don't think I've ever really understood what that is.
A simple progressive wave which is moving towards the right can be described using a cosine function, where
So, okay, so we know, excuse me, so we know that. So the function y with respect to x and t, so you're going to pass in x and t, I think, with respect to, is equal to whatever maybe the amplitude times the cosine of whatever k is times x minus whatever omega is times t.
y of xt is the displacement at position x and time t,
Is the displacement at position x and time t. So this whole thing is the displacement of position x at time t. Okay?
and a is the amplitude or maximum displacement of the wave.
Maximum displacement of the wave. So amplitude is, if I remember correctly, it's this. So this becomes the amplitude, and this would be a varying amplitude um, across the whole thing. But yeah, let me just so let's imagine the waves like this. This is the amplitude, I think, and this is the frequency, right? I think so.
This expression, we have defined the wave number k as 2 pi over lambda, where lambda
The wave number. I mean, what world do we live in? I don't understand. Why is it so like abstract? The wave number. Goodness me. Okay, well, I can't complain. So it's saying the wave number k. So okay, so this is important. So let's grab this, and then it's saying that the wave number k is equal to 2 pi divided by lambda, where lambda was what? Lambda was our h Planck over p, Planck over momentum.
is the wavelength, and we've also defined the angular frequency omega as 2 pi f, where
2 pi f, and f is equal to the energy over h.
f is the frequency of oscillation or vibration of the wave.
Oh, f is the frequency or oscillation, but that's because there could be something here that I'm missing. But okay, let's just continue.
Now, this displacement function is a solution to a general wave equation which takes the following form. It's worth noting that this equation involves partial derivatives, which are represented by the curly d symbol. In the wave equation, the displacement function y is a function of two variables, x and t, and so it's appropriate to use the partial derivative symbol when differentiating with respect to one of the variables. We can confirm that the cosine wave function is indeed a solution to this wave equation by substituting it into the equation. If we take the first and second derivative of the wave displacement relation with respect to time and space, we get the following relations.
Right, let's because this is where I stopped, I think, originally. So I got 7 minutes in. It says that the unsquared version. So this okay. So this is the first order version. This is the second order version. The first order version is equal to negative of k times the amplitude times the sine of these duraggies, and we can't derive that from this, but we are saying that. So if is he saying this is equal?
And relating it in sine wave, there is no rotation or vibration of the wave. Now, this displacement function is a solution to a general wave equation which takes the following form.
Is the solution to. It's the solution to. What does it mean by is the solution to in mathematics? Oh, well, it's worth trying. I I suppose there's a difference between something being equal to something and something being the solution to something. Though I suppose in a way, if something is the solution to an equation, it means that's after you've processed it. It is the solution, right? So after computation, this is the solution. So if this is the solution to that,
It's worth noting that this equation involves partial derivatives, which are represented by the curly d symbol. In the wave equation, the displacement function y is a function of two variables, x and t, and so it's appropriate to use the
okay.
partial derivative symbol when differentiating with respect to one of the variables. We can confirm that the cosine wave function is indeed a solution to this wave equation by substituting it into the equation. If we take the first and second derivative of the wave displacement relation with respect to time and
If we take the first and second derivative of the wave equation with respect to time, yeah, okay. So the first derivative is equal to negative k a sine, because a is okay. No, because so the derivative of cosine must be sine, and yeah. Okay. So actually, this is exactly what I was trying to do last time. I remember as well. Is I need to figure out differential equations, like how to solve them, because I think um that this is the output of taking the first derivative of this, right? I think so. In fact, calculate first derivative of equation. See if there's like a MATLAB sort of thing, or what's it called, Wolfram. Oh, that's interesting, isn't it? Haha. Okay, so derivative is like yx of t. So yx of t is equal to the amplitude of cosine times kx minus omega t. Kx minus omega t. And so let's see. The derivative ends up being negative ka sine. Negative ot differential of x. I mean, it could be. Yeah, we need to learn this. So this is absolutely highlighting problems in my understanding of differential equations, solving them and stuff. However, still, still pretty interesting is that this is the first derivative, this is the second derivative of this, and so it's saying that here though that this is the first, so the derivative of time. So this is with respect to x, this is with respect to time.
In space, we get the following relations. And then if we sub these
Oh, this is for x and this is for t, I see.
back into the wave equation, we find the following green expression. If we then divide both sides by y, we find that v squared equals omega squared over k squared. And therefore we see that this displacement function is indeed a solution to the wave equation, provided that v equals omega over k.
Okay, this is the perfect place to stop and the perfect place to start the next one. I think understanding something like this would be a massive advantage to everything from here on. So I'm going to stop here. That's really exciting to leave on actually as well. I'm looking forward to knowing this. What I'll do is I'll do some revision as I do, because I can't do this every day because I'm making a game as well. But in the back of my head, I'm just thinking about it. What I'll do is I'll go to a few pubs and try and work out differential equations and try and solve them and stuff. And hopefully I'll come back with a bit of insight on how to, or a few tips and tricks of how to solve them. Maybe we'll crack what's happening here. So let me just put a note in here to say, let's go for the next episode. We should. Oh, this is way too small. For the next episode, we should look at this video and try and solve the the differential equations from the original green part. Let's run with that. Let's also just do a quick Duolingo before I go. Because why not? Why not, I say.
Ναι, Κατερίνα.
Yes, Katerina.
Στο μίνι μάρκετ.
Stop.
Στο μίνι μάρκετ.
At the mini store. At.
Ναι, Μάρκ.
Nay, Mark. Yes, Mark. Carrot and water.
Καρότο. Και
Nero.
νερό. Το ρο σινεμά.
the pink cinema.
Άννα και Μαρία.
Anna and Maria.
Κατερίνα και Κάρμεν.
Caterina
Κατερίνα και
και Carmen.
Κάρμεν. Το ροζ βάζο.
The pink vase. Yes.
Ναι, είναι
Είναι rose.
ροζ. Κάρμεν, το νερό.
Carmen, the water. At the mini market.
Στο μίνι
Mini
μάρκετ. Ρύζι με καρότο.
Risi
Ρύζι. Ρύζι με καρότο.
me
Καρότο.
rice at with carrot.
Ναι, βαρβάρα.
Yes. Vavara. Can't remember what that is.
Βαρβάρα.
It's a name. Yes, Vavara. Rice.
Ρύζι.
Risi with me
Με
carotto.
καρότο.
Caterina,
Κατερίνα
και
και
Carmen.
Κάρμεν.
Good. Awesome. That's it. I think we'll pick this up soon, but not too soon. There will be a point in time when I start to thrash out on this, like pretty hard, but I'm doing that for this game I'm making at the moment. I don't have enough time to share between them two, and I feel like the game. I kind of hope it makes a bit of money, to be honest, because it's a lot of work gone into it, and it was nice to be able to support some of this other work that I'm doing. That'll hopefully help us all as a world. I think the priority has to be the game. Also, that the game helps me understand Unreal Engine more, and quite frankly, I think Unreal Engine is a great way to simulate some of the things that I'm trying to achieve. So, with that said and done, I shall bid you farewell and have a lovely evening, morning, afternoon, or whatever. Keep learning, keep loving. Speak to you later.